The Martian soil has known wheels, blades, arms, and even sensors, yet nowhere upon the Martian regolith has a human stepped foot. While we're not there yet, the Expanse rover will be a critical step forward. Its full form is extraction and prospecting of aqueous and nutrient-rich subsurface environments. Specifically, it will perform in situ resource utilization using subsurface Martian ice and investigate the terrain through analysis and sample collection. With this new Expanse, we move closer than ever to putting humans on Mars. We are the 2025 NASA Seas Mars Rover Resource Utilization Team, and we will be presenting our proposed Mars Rover mission. But first, let's meet the team.
I'm Vedaang Verma, a junior at Bridgewater Raritan High School in New Jersey.
I'm Hernandez, a rising senior at Holy Trinity Episcopal Academy in Florida.
I'm Itzel Echevarria, a rising senior at Boris Senior High School in Idaho.
I'm Mayhew, a senior at Legacy Magnet Academy in California.
I'm Dhruv Mantri, a junior at Cypress Ranch High School in Texas.
And I'm Tchira, a senior at Dr. Michael Lamcrop Senior High in Florida.
Let's start off with the background on the Martian conditions. Mars is extremely cold with an average temperature of negative 63 degrees Celsius. Low temperatures can compromise rover battery performance and inhibit human habitability. Moreover, the atmosphere of Mars has been significantly reduced to about 0.6% the thickness of Earth's. Landing massive objects becomes more complicated and dangerous due to less atmospheric drag, and this poses concerns for crewed missions. Additionally, thin atmosphere means greater exposure to radiation. While Mars may have hazardous conditions, it also has some key resources, namely water ice, which shows up on the surface mainly near the poles, but is plentiful under regolith in certain areas. Due to the low pressure, ice can sublimate when it reaches the surface and even make ice clouds. Finally, there has been evidence of ancient water on Mars in its earlier periods, with water-related minerals and geologic features. This points to the question of past or even present life on Mars.
Mars's geologic history can be divided into three periods: the Noachian, Hesperian, and Amazonian. The Noachian period presents a warmer and wetter Mars where liquid water once existed. This is the most extensively studied. The Hesperian period presents a rise in volcanic and tectonic activity, but a decline in surface water. This period, Mars cooled and lost most of its atmosphere. Finally, there is the current Amazonian period, which is geologically dormant, though it has significant features associated with water ice. These include glaciers, polar ice caps, and low-grade debris aprons.
Let us now understand why it is so important to explore Mars. Firstly, Mars offers an insightful point of comparison for how rocky planets form and develop over time. Geological processes on Mars can mirror those of Earth's. Moreover, ancient Martian terrains can clue geologists about Earth's past. Secondly, Mars can help answer one of humanity's most pressing scientific questions. Is there life outside of the Earth? Mars is a great candidate for its past activity of liquid water. A very critical reason for Mars exploration is to prepare for human habitation on a new planet. Specifically, this involves in situ resource utilization, or ISRU, which means harnessing local resources and avoiding the constraints of hauling them from the Earth.
Let's now discuss some previous expeditions to Mars, including their goals, timeframes, and regions. The NASA Mars Exploration Rover mission consisted of two rovers, Spirit and Opportunity, which explored Gusev Crater and the Mariani Planum respectively. The mission was extended several times to last 14 years, aimed at finding evidence of past water through Martian rock and soil. The Curiosity rover, which is currently on Mars, has been assessing the habitability of ancient Mars since 2012. The landing site for this rover was Gale Crater. Finally, the Perseverance rover, plus the helicopter Ingenuity, have been searching for ancient microbial life since 2021. They are exploring Jezero Crater as of now. Overall, these previous missions have proven effective, but they have focused mainly on older age terrain as opposed to modern Amazonian features.
Based on our research on Mars conditions, history, and previous expeditions, we came up with three key mission objectives. The first objective is in situ resource utilization with water ice. We plan to feasibly mine this ice with depths up to 5 meters. We also plan to use electrolysis to separate hydrogen and oxygen in the water, enabling renewable energy and breathable air. Overall, this objective will be essential to preparing for future crewed missions, providing resources for humans to stay on Mars. Our second mission objective is to analyze stratigraphy. Mars features geographical features from many different ages, but relatively less study has been done on more recent Amazonian geology. Examining terrains of varying age will be key to understanding geologic evolution. Our third and final objective is sampling and mapping. Our rover should be able to take high-resolution images of notable features and also collect valuable samples. Looking for biosignatures is also imperative. Based on our objectives, we collaborated as a team to propose an array of landing sites and to evaluate these landing sites on their scientific value and feasibility. Specifically, we used three main metrics: environments, constraints, and targets. Environments include valuable geological regions that we decided to look for in a landing site. A solid candidate has important features like remnant glaciers, ancient lakes, craters, and more. Constraints are limitations of the landing site for the sake of feasibility. A landing site must have a low elevation, smooth terrain, and ample space for a landing ellipse. Now, targets are the specific resources we are interested in, such as water ice, both surface and subsurface, olivine, sulfates, and more. We evaluated all of the landing sites on a matrix to provide an overview of how each one stacks up with the metrics. Similar matrices have been used in determining landing sites for previous Mars rover missions. After careful consideration, our team settled on the landing site of Deuteronomus Mensae, a fretted terrain near the Martian dichotomy border. The area contains many glacier-related features, such as lobate debris aprons and lineated valley fill. Subsurface ice of 1 to 5 meters has been confirmed in this area, and its protection from radiation under regolith provides hope of biosignatures. Moreover, this region provides terrain across ages, containing Noachian highlands, Hesperian volcanic plains, and Amazonian glacial features. Finally, the landing site fits within our constraints, having a low elevation and providing lots of space for a landing ellipse. Now let's move on to the instrument payload of our Expanse rover. This is a CAD model of our instrumentation on top of Perseverance's drive base. Notable features include the ice drill and the PEM electrolysis module, which are custom subsystems. Our rover is powered by a radioisotope thermoelectric generator. The Deep Ice Geological Investigation Tool, or DIGIT, is a custom mechanism that is designed to mine subsurface ice of up to 5 meters of depth. Firstly, the arm of DIGIT consists of 3 separate pivots, designed to reach over obstructions for accurate positioning. All of the joints are motorized, providing precise control and modeling after previous rover arm designs. In order to reach the necessary depths, a 2-stage telescoping arm is used to extend the drill bit, which is a helical auger design, allowing the continuous shift of material up and out of the drilling hole. Throughout the design, high torque actuators are used. This ensures enough strength to break through rock and regolith that may be on top of or mixed in with the ice. Overall, DIGIT is designed to work with our rover design and mission objectives. It can reach great depths while remaining folded on standby. It also directly fulfills our ISRU objectives.
Once the rover drills through ice, a pressurized and heated tube intakes the crushed ice into the PEM electrolysis, at which point it melts into liquid water. But before the water can enter the electrolyzer, it needs to be purified first. Once the water passes through the purifier, it will be moved with a transfer tube to the electrolyzer. PEM electrolysis essentially uses electricity to split water into hydrogen and oxygen. Water is fed into the anode and oxidized into protons, electrons, and oxygen. The oxygen leaves the system while the protons cross the membrane and electrons travel through the wire, both arriving at the cathode. Here, the protons and electrons combine to form hydrogen, which exits the system. This process is significant as it applies ISRU on water ice for real capabilities in a crewed mission. It can provide hydrogen as a power source, oxygen as breathable air, and drinking water.
SAM analyzes the chemical and isotopic makeup of Martian rocks and air. It detects key gases like carbon dioxide, methane, and water vapor, critical for supporting ISRU planning. It also looks for organics and measures isotopes to help determine the age and origin of materials. These insights guide how and where we might extract useful resources on Mars.
RIMFAX is a ground-penetrating radar that sends radio waves into the Martian surface and records reflections to detect subsurface features like layers or water ice, up to about 10 meters deep. In 2021, it successfully mapped underground structures in the Jezero crater, helping scientists study Mars' geologic history. The chart on the right shows how RIMFAX switches between 4 modes: surface, shallow, deep, and long integration, to detect targets at different depths. It adjusts settings like receiver window, gain, and processing power to improve signal detection as depth increases. The NavCam, or navigation camera, is an imaging tool used for autonomous navigation, capturing wide-angle images of the environment. It will be essential to our mission in many ways. Firstly, it will map out the environment to determine safe and efficient pathing for the rover. Moreover, its ability to generate 3D visualizations of terrains will identify geological regions of interest. Secondly, it will be able to aid in positioning Digit to avoid obstructions. Finally, it will provide visual documentation of several phases of the mission. This design is lightweight of less than 300 grams and low power of less than 3 watts.
One major part of our mission design is the 2 helicopters we plan to implement with the rover. Our helicopters are inspired by the Mars Ingenuity helicopter, but are designed with modifications to fit our mission goals. The primary advantage of using helicopters is that they can go much faster than rovers. While rovers can only go about 0.1 kilometers each day, each of the helicopters can move at about 0.7 kilometers a day. Our first helicopter is called Romulus. Romulus is powered by a rotational solar panel that has the ability to keep dust off. Just like Expanse, Romulus uses NavCam, but at a small scale, used for both navigation and imaging. An IMU, or inertial measurement unit, consists of gyroscopes, accelerometers, and magnetometers, ideal for relative positioning. The alpha particle X-ray spectrometer will be used for surface mineral analysis, specifically determining the chemical composition of minerals and soils. With its analysis, rover pathing can be determined and resources can be found in the regions of interest. The spectrometer emits alpha particles that cause atoms to emit characteristic X-rays. By analyzing the energy levels of the X-rays, the element can be determined. Additionally, since the spectrometer needs to be close to the subject, it will be used each time the helicopter lands. The second helicopter is called Remus. Just like Romulus, it is modeled after Ingenuity and has a rotational solar panel, NavCam, and inertial measurement unit. In place of the alpha particle X-ray spectrometer on Romulus, Remus has a return-to-Earth camera. This camera was flown on Ingenuity and provides color images that are of higher resolution than the NavCam. This instrument can take detailed images of the Martian surface and then downlink them, returning them to Earth. These images can be analyzed on Earth, and Mission Control can use them to determine pathing and the value of various ROIs. Additionally, this camera will be essential for publicity. It will offer high-resolution, color documentation of the mission to foster public interest and secure continued funding.
Now that we have covered the rover design and instrument payload, let's dive deep into the specific mission path and regions of interest. This is the outline for the mission path. In the center, there is a 38 by 25 kilometer landing ellipse. The large area accounts for potential error in the entry, descent, and landing, or EDL for short. On the map, regions are color-coded based off terrain classes, with green area allowing for smoother and quick traversal, and red areas being untraversable by the rover. The black line shows the rover path, while the pink and blue dashed lines show the paths of the helicopters. The mission path was determined based off of key constraints and targets.
Region of Interest 8 is the first stop for the Expanse rover, located about 28 kilometers from the center of the landing ellipse. The primary interest here is the tongue-shaped lobate debris apron, which is interpreted to be from a remnant Amazonian age glacier. This is valuable for analyzing the often understudied Amazonian climate cycles. Additionally, this region has high ice content, ideal for Digit's ice mining and ISRU. It is classified as a high-interest sampling site.
Region of Interest 2 is located approximately 9.5 kilometers from the landing ellipse. This region is abundant in silica-bearing clays which are formed from water activity. Silica clay-abundant regions have been common targets for previous missions for their ability to preserve biosignatures. This site also has notable subsurface ice consistency and an elevation change of 100 meters. This region is classified as a high-interest sampling site.
The last confirmed stop on Expanse's route is ROI number 1, located about 50 kilometers from the center of the landing ellipse. ROI number 1 is the lip of an Amazonian crater, and specific dating can be done with SAM. The crater is untraversable for the rover, so imaging will be very important. This region also shows 100% ice consistency, and it will be great for ice mining and ISRU. It is classified as a high-interest sampling site.
ROIs 4 and 10 will be covered by Remus, and they are located 45 and 42 kilometers from landing, respectively. This region is Hesperian age chaos terrain that is extremely rough and hilly. For this reason, it is logical to perform drone scouting as opposed to rover traversal. This area also contains a series of ice-rich deposits. If a drone finds interesting targets, the rover can travel to the region to perform ice mining and sample collection, specifically at Site 4, since Site 10 is too difficult to traverse. Site 4 is a high-interest sampling site, and Site 10 is a medium-interest sampling site.
Romulus's first stop is ROI 3, located 27 kilometers from landing. The peak is too steep for the rover to traverse, but it can be examined by the drone. Moreover, this region has a 75% ice consistency for depths of 1 to 5 meters. Should it be deemed necessary, the Expanse rover can move to this ROI. This is classified as a medium-interest sampling site.
The final stop for Remus is ROI 9, 42 kilometers from landing. This is interesting impact crater with a rim that is untraversable by the rover, but feasible for drone flight. The main interest in this site is a spike of concentration of hematite. This anomaly was possibly revealed by the impact. This is classified as a high-interest site and is not for sampling due to traversal constraints. This is a diagram of the mission timeline. The first portion of the mission after landing will be preparation and diagnostics. Both the rover and the helicopters will need to test and make sure all the subsystems are operational and weren't damaged during EDL. Communications from mission control will confirm the commencement of traversal. As evident in the timeline, much of the time is spent in transit, accounting for the speed of the rover and helicopters, as well as the conditions they'll be traversing. There will be periods of 5 sols at each ROI to take images, collect samples, analyze terrain, and much more. At a certain point, all paths will be data dependent on the findings at Doodle Mense. The rover and helicopters will rely on instructions from mission control.
While we have done extensive work on our mission and proposal already, it is important to look ahead on how we can continue the project. It is important to conduct a deeper analysis on Deuteronomus Mense, verifying the traversal, the region of interest, and landing ellipse. We are currently looking to putting together a high-wish proposal so that we can get a more detailed imagery of the landing site. It would also be critical to develop a full rover design, using a custom drive base rather than Perseverance's, and creating a detailed electrical schematic. Finally, it would be helpful to prototype some of the custom instrumentation at a small scale. Digit's ice mining system and the interaction with the PEM electrolysis module should be tested for a more complete proposal. We should also make sure to enhance our documentation of both our previous and continued findings.
We would like to thank our mentors first of all, S.J. Ralston and Todd Hefflinger, who have been a key part of our SEAS journey and have devoted countless hours to supporting our project. We would also like to thank Selena Miller, Laura Tomlin, Margaret Baggio, Dr. Kevin Cosby, as well as the Center for Space Research at UT Austin and the entire NASA SEAS program.
SEAS has been a once-in-a-lifetime opportunity that has taught me so much in a matter of weeks. Both the interns and the mentors have been extremely supportive, and this experience has solidified my love for STEM and excitement to pursue a STEM career.
The SEAS program has taken my love for space and science to real applications. I have collaborated and connected with amazing individuals, all while honing my skills in a variety of softwares.
NASA SEAS has been an experience that has taught me much beyond the classroom. It has immersed me into a community of like-minded individuals who both challenge and guide me. Particularly, our mentors guided us through research, but also helped shape us as people.
NASA SEAS has been one of the most memorable experiences for me. While I was nervous at first about immersing myself into a group of intelligent scientists and students, I grew to be part of an amazing team with supportive mentors. I am grateful for the connections I made.
NASA SEAS was a once-in-a-lifetime experience. From working on real-world research to learning from astronauts and mentors who truly cared, every moment fueled my passion for science. Collaborating with driven students pushed me to grow and left me confident, inspired, and ready to shape the future.
NASA SEAS has been an exciting chapter of discovering new passions and people. I've unlocked new skills and interests, including analyzing GIS data and payload design. But beyond this, I've been able to meet people of remarkable intellect and character. I'm sure this experience will prepare me for a future in STEM.